the sup-norm problem. I've worked on this for a long time, but I haven't talked about it in a while, so that's why I will start slowly and hopefully get somewhere in the end. So what's the sup-norm problem about? It's a bit parallel to the quantum unique ergodicity thing that we heard in Aspion's talk. So very classically, we could start with a Riemann surface which is compact and no boundary. And so on this, this X is the surface and G is the Riemann metric. So G gives rise to the Laplace-Beltrami operator. And then by spectral theory, we know that if we decompose the L2 space, then we have a spectral expansion. Well, so we can find these eigenfunctions of the Laplacian. And we have eigenvalues lambda j, and we want to, so classically one wants to understand how these eigenfunctions behave when the eigenvalue gets large, and so, yeah, so that's the sup-norm question. The question is, so what can we say? Very informal, what can as lambda j goes to infinity. So is this bounded, or you can wonder? And just to maybe, so in the setting of Aspion's talk, he took these guys and put them, so when the L2 normalized, he put them in front of the volume form, and so he had a sequence of measures, and he was asking how this distributes. And basically, here we ask also about the distribution of these guys, but we focus on high peaks and not on qualitative distribution properties. Okay, and then in this setup, there's been a lot of work from the harmonic analysis community. So as I said, this has been studied for a long time, and maybe I can't name everybody, but I think it started with Levitin and Avakumovich, and then there's a lot of work, and maybe a nice exposition that I like is to Seger and Sorge, and the result is that this is bounded by lambda j to a quarter. So I always have, so you can either normalize the L2 norm, but of course you have to, or you carry it around, what you prefer. So this is the classical result, and it's sharp if I don't make any restrictions on my Riemann surface, because it's known that for the sphere this is obtained. Right? But I'm not so much interested in this general setup. I feel I identify as an analytic number theorist, and we like very much different surfaces. So I hope nobody disagrees with this. When I say number theorists, this basis xq, where I take the upper half plane and I mod out gamma naught of q. I think we've seen this week, so I will not write this down. So before anyone complains, I'm aware that these are non-compact. But still, we like them very much, and we still have a Laplace operator acting on this, and we have a spectral expansion. The spectral expansion is more complicated than this, so we will focus on the cuspidal part. But for the cuspidal part, we can ask the same question. So for the in particular, if we fix our Q, then the same bound will hold for cuspidal eigenfunction. So we consider kind of lambda j to a quarter to be the baseline bound or the local bound, because it kind of follows from this bound doesn't use any global information on x, it works purely locally. So we sometimes like to call this the local bound. Okay, so this holds. As pointed out by Asbjørn, we gained this additional Q to play with. And, well, if we have more than one parameters to play with, things get a lot more fun. So let me say what the goal then is. So maybe making this question more precise, the goal is to show for phi we want to show so we want to have like bounds on the sup-norm where we get good polynomial dependence in lambda and q simultaneously. And of course,
still stick to eigenforms, right?
yes, I mean, okay, if I phrase it like this, I mean, it's always a Laplacian. I'm always talking about Laplace eigenfunctions.
Yeah.
Phrased like this, of course, I can consider non-eigenforms.
No, I meant Laplace eigenfunctions.
Yeah, so, and lambda will always be Laplace eigen. But like this, it's maybe not well phrased because we have also seen this in Asbjørn's talk, that we can say x1 is the classical modular surface, and we can kind of take a function on the classical modular surface and just view it in here. And, well, then we will not gain any interesting things in Q, right? So I should really restrict to new forms here. And in particular, now we have not just the Laplace eigenfunction property, but we also talk about Hecke eigenfunctions. So now we are in a very arithmetic setting. We just look at functions that don't come from any xq smaller than this, and we have eigenfunctions of all Hecke operators and so on. And then we can ask this. I should say the alpha here depends on how you normalize the measure. So let me say this. So we take the normalized the measure to be. But if you prefer any other normalization, you just have to rescale and work out the new alphas. Okay, so what is known in this setting? I will review some results. There has been done a lot of work there, and I can't mention everybody, so this is kind of, I'm surveying my favorite results, and I hope not to offend anyone that is left out. So, kind of the local trivial bound is alpha a half and beta a quarter. The quarter comes basically from making this work in a non-compact setting, and I will come back to this. But the first real breakthrough which started this whole business is due to Ivanic and Sarnak. And when was this? 90s. Where they get beta a bit less than a quarter. And here it's crucial now that we work with Hecker eigenforms. It's used crucially in their proof. And if we add then we can. So basically, the Ivanic-Sarnak argument is written down for Q equals 1, but you can run it through for general Q and keep track of things, and then this is worked out here, and you get a half.
Is beta looks weaker than... Ah, no, sorry. No.
So they prove more. They prove also different results in alpha, but I will just mention this. And and I think it's Q's. Okay, and then this kind of started a lot of work that happened then from 2010 to 2000 till now, basically. And the next big kind of milestone is due to Templier around 2015, and this is also based on a lot of where they can take alpha to be a third, and now this is important for Q. Square free. So Hakosh-Templier studied the level aspect for getting the eigenvalue, and then the hybrid version published by Templier alone in 2015 roughly. And then the most recent one that I want to mention is due to Nelson, Kayutin, and Steiner in, I think it was published in 23, right? And this is again for Q square free. And here we can take alpha a quarter, and unfortunately the beta is not that great, but I think in follow-up work Steiner had worked out that you can take 3/8, which is worse than a quarter, but the focus here is on alpha being a quarter, which looks kind of nice because we had beta equals a quarter there. Anyway, this is as far as I know, this is the best result in the square-free setting. Okay. And so I really want to highlight that for these two results, and probably if you want to go past a half, the square-free assumption is very important. And things are slightly different if we move to non-square-free levels. So that's what I want to do now. And of course there's the expectation that has, so let me just say what's the expectation first. If we allow, or if we take Q to be a prime power, so this is the opposite of square-free, because now we fix one prime and we go up in the powers. Then we expect the situation to be very similar to the Archimedean, the spectral problem. Then for the look more similar to the spectral aspect. And then we noticed that in the spectral aspect, we kind of started with a quarter and we were happy going below a quarter, while in the level, we kind of started at a half and we went down to a quarter and we were very happy with this quarter here. This is a big result. But now, if we kind of go away from the square-free situation, we expect we would like to want to start at a quarter and then try to go below. And this is actually then spelled out in work of Simon Marshall and Abhishek Saha. I think 16 and where they show that basically so if Q is a square, then the correct, we can actually really start at a quarter and this expectation kind of becomes true. And this result is a bit more refined. It applies to all Q, but to state this so more precisely, they show that so kind of to state this, we have to separate the square-free part from the square part. And then we get these two different exponents now. And if we are square-free, then Q0 is 1. So we end up in a situation of Harcosh and Templé. And if we have a square, then we get a quarter of the level, which is what we call the, which in the setting is maybe the local bound. And now, so this is the results I wanted. Yeah.
So what is the conjectural best bound? Is it alpha beta equal to 0? Or?
No. Let me answer this in a second. 5 minutes.
And here Q1 and Q0, they are primes or square free?
No, this is now any Q. We just write it as like this. We kind of write it as, so this is square free, and this is, yeah, the square. See, this is the maximal square part that you can take out.
Can I also ask, what is the expectation based on?
Because when you...
Is it just experience or
well,
computational?
experience, but also when you do the spectral aspect, you kind of do harmonic analysis over the real, over the Riemann surface. But if you would write this adelically, then in this case you would have analog things just over QP, where when the P is fixed, this will behave similarly, hopefully. I mean, it does in a lot of places. So.
Sorry, so is Q0 also square free or not?
No. So you take your favorite Q, and we take the largest square in it you can find. That's this thing.
But so the level could be like a very high power of a prime as well.
Yeah.
Okay.
All right, so actually one can, if we don't care about the third there, so if we just want to prove, say a quarter here somehow, then there are a lot of ways to prove this. And before I state more results, let me talk a bit how would one prove this here. So I think that the community on the sup-norm problem was very biased after the work of Ivanic and Zanak, and they've used what's called the amplification method, and a lot of the papers have actually just used the same and adapted it to the setting. But a lesson that we've learned in the last years maybe is that if we are on these spaces XQ, they are non-compact, so we have a Fourier expansion, and so we should use it. Before you start any fancy shenanigans, maybe we should just write down the Fourier expansion and see where it gets us. So if you learn nothing from my talk, maybe you should try the Fourier expansion first. And to set this up, maybe we have to kind of slightly change our setup a bit. So first I replace phi in L2. We replace this by, say, phi tilde of z, which is, so this is just a renormalization. And this little trick actually goes back to Simon Marshall. At least it appeared in his paper from 2016. And then we note that now phi tilde is invariant under, say, but I will write down what this group is. So this is basically matrices. So we kind of balance this out. The gamma naught of Q, we would have the Q all here, and scaling it kind of balances this out a bit. And this just looks nicer. And it really helps you in the technical details. And then we kind of, I can state the lemma. Which is basically Zaha, myself, and Thomas plus epsilon. But probably it's quite natural that one should expect something like this. So, and now we take Z in F1, and F1 is the fundamental domain for the modular curve. So if we would be at level 1, and this would be our fundamental domain, and we could go everywhere. Now, this doesn't help us to bound the sup-norm of everything. So we have also to take but we can cover the whole space kind of by taking SL2Z translate. So now if we take our phi of sigma set, we can go everywhere, right? So we want to bound this.
Phi or the renormalized phi tilde?
What's that?
This is phi or the renormalized phi tilde? No, this one. You take the phi or the renormalized?
Thanks. And then we get, epsilons. And two terms. The first term is okay, so the first term.
Can you spell out what you wrote?
So this phi tilde thing of evaluated that Z translated by our matrix sigma is bounded by, some safety net that like epsilon power, and then it's Q1 times Q0 times lambda to a half divided by the imaginary part of Z, and then everything to a half. And I will write the second term. This is now Q0. The sixth. And, okay, this is the result. And I will make two remarks and answer, hopefully, the question. What is the expectation? So,
and that's independent of sigma, right? You wrote sigma on the left, but sigma doesn't show up on the right, so it's
this is on purpose.
Okay.
I think Mark will. So first, maybe we should kind of, from this we already get this quarter result here if we ignore Q1, because so Z is an F1, right? So the imaginary part is bounded from below. So we can estimate this away. And here we actually have lambda to a quarter, Q0 to a half, which is roughly the level to a quarter. So this is the worst cases. If this is of size 1 and we recover basically ignoring Q1 and beta 2, which is nice. Okay, then maybe what goes into this is, if we forget this sigma, then actually you can remove all this business there, because in the Fourier expansion you just have Hecker eigenvalues and you can estimate everything nicely, and you would not see the Q's. But because we have the sigma z, what's in the background here is that we use the Fourier expansion at different cusps. So we have to understand the Fourier coefficients at different cusps, and they behave quite differently, and so one picks up these Q's. So we use at all cusps. And then maybe finally, I would expect that this is the correct size. But this comes from behavior of the Whittaker function very high in the cusp. So kind of you have two kind of regions when you look at your cusp forms in some like fixed set which is in the middle of H, then you would actually expect this to be zeros. But as soon as you go to the cusps, you get this like this weird behavior, which would be the correct size. Okay.
Where does this normalization play a role? I mean, it only gives you at infinity, it doesn't change the...
It just changes the where you are. So basically, you can look where I goes.
Yeah.
So actually, if you look at this at I, you're actually at height. So you just kind of shifted things down, and then this kind of captures more where the Fourier expansion goes on. Because, okay, now our goal is still to improve on the quarter, and we see that this Fourier expansion wins as soon as the imaginary part of Z is, in this normalization, is a bit high in the cusp. But we will lose when we are close to 1, so there we have to do something different. And this renormalization kind of just shifts you in the right range where to do things. And it's nicer to work with this. If I have time, maybe I will say something about this. All right, so if we want to improve alpha, we have to do something. Different if is small.
Sorry, what does small mean? Does small mean
Well,
1 or?
depends on how ambitious you are, of course. I mean, basically, you just have to kill whatever. Like if you aim for the 5/24, you just look at what you need there.
I think it means not too big, not in the sense that it goes.
Would 1 qualify as small?
Yeah.
Okay.
Not too big, yeah. Basically, I think the way one can think about it is you try it for the imaginary part being 1, and if you get something meaningful, you just make it explicit in your imaginary part, and then you try to optimize.
It can't be too small because you're limited to F1.
Yeah, let me change this to not too big. No. Okay, so we want to do better. Now let me state the theorem. Which is due to myself with Radu, Thomas. So now we restrict to Q being a prime to a power 4n, and we exclude 2. Then so this is again a new form. And we allow our constant to depend on p. So this is like a true depth aspect thing. And we get, and that's why I like this result. Because it's very uniform in Q and lambda. And this is exactly what we would expect if we really work with high prime powers, then we should see the exact same thing as we see in lambda. And maybe I should say that this is something similar was obtained in the work of Zaha and Hu. They have an analogous for compact. Like in the setting that Aspion then was stating his theorems, you had like a quaternion algebra and then you have some level. And in this setting, something similar was obtained by Zaha and Hu. But if we're really in the classical setup where we mod out gamma not of Q, then this is the theorem. And before there are maybe questions, one can actually, so the same methods allow us to show that so the rad of Q is just the product of all primes dividing Q, and you get some power of this, like for some A, which is whatever, and then you get this thing for general Q. But of course, if you run through square free things, then this radical is Q, and then this would be worse than all the other results. But as soon as you kind of allow it to become square full, then this is the nice behavior we see. And one can probably, like, A is not that large. It depends on how hard you work, but 4 is easy. Maybe if you want to get this to 1, it's harder. And you will never get something like a quarter there or whatever. So, I don't know, we haven't tried to optimize this.
The only point is that this is by 4. Let's say if Q was P to the 4n plus 2, you won't...
Yeah, that would be still fine without this. It's just that we wrote this paper for a different purpose, and for exposition we made this assumption. So this is what you should think, but in the paper it's written this. All right, and I have 5 to 10 minutes to talk about the proof. Okay, so we had the Fourier expansion. Or should I? All right, so comments on. So we already agreed that we only have to look at imaginary z not too big. And so in this case now, because we know what bound we're aiming for, we can just see when is this thing good enough so that we win already. So it's sufficient. Look at of bounded by q lambda to a 12. So this is what not big means for us. But actually, even z equals I will tell you a bit about what's going on. So. Okay, and then we are now in this. So for us, q is p to the 4n, so that just to state something obvious. And if we look at this group here, it now becomes very balanced. And inside there, we have the principal congruent subgroup. So this is the, if you want, the kernel of the reduction map mod Q not. So this has index roughly Q naught squared. So these are the indexes. And I will start to lie a bit now, just to maybe, but I think it illustrates the point. So let's be wasteful for a second, and we have this phi tilde, right? It's invariant under this thing, but it's of course invariant under our principal congruent subgroup. So let's forget this for a second and work with this. And So let observe there are roughly not different elements, or maybe even I should say orthogonal in that have the same Hacker eigenvalues. And of course, and maybe a Hacker eigenvalue is that something that's easy to define when you're congruent 1 mod q 0, but the point is that they're kind of different to tell apart from your phi tilde. So when you just know the Laplace eigenvalue and all the Hacker operators, we really have q not different guys here that we can't really tell apart, obviously. Right? So what actually goes on here is that, so these are and so what really happens is that the nice thing about the principal congruent subgroup is that it's normal. So we can act on our functions on this space with SL2Z, and we will obtain something in there. So we actually, what's going on here is that phi tilde generates irreducible representation V of SL2 of dimension, which is roughly Q naught. This is already, if you take n equals 1, then this is, no, this is never nice. So this is not a nice, so this group has, so this ring has 0 divisors, so this is not, but of course it's a finite group, but it's nicer when this is prime. Anyway, we have this V, and the idea,
n is 1, your q0 is already p squared by your assumption.
Yeah, p squared would be the interesting case when this is. Sorry, I got confused. So, maybe because the time is running out, I will just say, if we use, so we want to run the amplification argument of Ivanich-Sarnak in some form, and if we do this for this space, we lose miserably because we've done this stupid thing where we lost something, and we kind of ignore that we have all these forms that basically we can't tell apart. But what one can do is, one can take, so this phi tilde corresponds to a very special vector in this representation, and we can form the matrix coefficient of this representation and insert this in our argument. And this helps us to, so by some sure orthogonality, this helps us to project on our vector. So the idea now is to use a matrix coefficient. Of V to if to build a good approximate, or a good, let me just say a good projector. And if one does this and one estimates this matrix coefficient trivially, one ends up with a quarter, basically. So this is not enough, and so one needs to make then everything work, we need good bounds on this matrix coefficient. So we have to know how it decays. Of course, this matrix coefficient, if we normalize it correctly, will be 1 at the identity somehow, but it will decay, and we have to understand how this decays. And this is, if you're in this prime power aspect, this is a purely local problem, which is similar to things that you would encounter over the real numbers. So this is where you basically do periodic harmonic analysis if you want. And in the last minute, then, so you've set all of this up, you know your bounds. They've been worked out by Zaha and Hu. So this then all boils down to a counting problem, and I just want to state this finally. And I just want to write down what one has to count. So basically, one ends up counting matrices with integral coefficients such that this U guy is just a point pair invariant on the upper half plane, so it's gamma z minus z possibly squared, I think, over the imaginary parts. And we want determinant n that we have to consider something that's not in SL2 but has determinant comes from the amplifier that I didn't mention. But one has to allow this if you want to go better than a quarter. And we need then divisibility conditions where L divides so L is some divisor of Q naught, and then one gets this counting problem where this is the upper left, the upper right entry of this matrix, and this is the lower left entry of this matrix. And sigma was our, is it still somewhere? Sigma is something in SL2. And this would actually be, if you ignore the sigma, then this is a counting problem that was basically obtained by the work of Harkosh and Tompe, so they count stuff like this, and this has been refined. But as soon as you enter this matrix sigma, you kind of mix up the entries of your matrix gamma, and this makes keeping track of this congruence condition quite difficult. And the point is that you have to win an L. So you have to count this, and you have to win an L to counter kind of the estimates that come from your amplifier. But we had to think a bit about this counting problem, so I'm quite proud that we could count this in the end. And that's why I wanted to finish by writing this down. Yeah, thanks for listening.